Greetings. This is the fourth part of a series of, I suppose, videos, lectures, whatever you want to call them, that are about metaphysics, and in particular my desire to sort of rewrite that curriculum into something that makes more sense in the modern times. I've been covering a number of topics. I guess I started off with relations and went on to quantities like mass and velocity, and talked about how they fit into the metaphysical picture, particularly in the sense that some of them are relative terms. They are relative to one's state of motion in particular, and that's something that metaphysics needs to understand and needs to include. Now, I then went on from there, and now today I want to talk a little bit more about the idea of holism and where it fits into quantum theory. The first thing to say is that holism goes back a long way. When one now thinks of it, one can trace it, the idea of it, back into the very ancient past, to the first philosopher, really, Heraclitus, or one of the earlier philosophers, Heraclitus. Heraclitus said, "For those who have heard not me but the Logos, wisdom is agreeing that all things are one." Now, this oneness is often a theme or an indication of this idea of holism. But it's not quite there, and it's not quite unambiguous. But from there we can move forward into Nicholas of Cusa. Nicholas of Cusa said, and this comes much more closer to the idea of holism, "A part is not known unless the whole is known, for the whole measures the part." Now, this theme resurfaces in German literature and in philosophy of the 19th century, and particularly in Hegel, into the idea that, and this is the form in which it will be familiar to you, the idea that everything is connected. Everything is connected to every other thing in the universe. That, in other words, the universe is a whole, and the parts of it can only be understood in terms of that whole. Now, the idea of holism still had not been properly enunciated at that point. The idea of holism was really formulated by a South African general by the name of Christian Smuts. Let me see if I've got his name right. Jan Christian Smuts. And he wrote about this in a book called Holism and Evolution. It is apparently the first use of the term holism in the literature. Holism and evolution. And his idea was the various parts that make up a creature, a human being in particular, for example, or an animal, say take a lion. The parts that make up that creature are insignificant in regards to the whole. They all contribute something, but the whole is much more than the sum of those parts. The evolution is, I think this is Smuts' idea, is acting on the individuals. It's the individual that is fit or not fit, and does so in virtue of these parts, which are selected, as it were, along with the individual. So the individual is selected, and that makes for all of the parts of the individual to be selected alongside. And this also applies to plants, to everything that's living. So the idea that Smuts had was that the living world, the world that we understand through evolution, is more than the sum of any of its purely mechanical parts. That's how the word holism got into the literature, as this thesis about the organism, the being, how things are in themselves as organisms. So in 1890, the classic phrase that defines holism was formulated. The whole is greater than the sum of the parts. The whole is greater than the sum of the parts. And that is clearly the sense in which it's meant in Smuts's slightly later book on holism. So you have the classic line formulated before the word itself. So that was formulated by a psychologist, the phrase, the whole is greater than the sum of the parts. It formed the basis then of what is called Gestalt psychology. You see the whole, you don't see the parts except as they are subservient to the whole. The whole is greater than the sum of the parts. When you see, if you have a look at the classical optical illusion, or paradox, some people would call it, where you have a duck and a rabbit in one picture. You can see the picture as a duck, you can see it as a rabbit. The whole thing that you see, duck, say, is greater than the sum of the parts, because the parts would also make up rabbit. So if you see the duck, you're seeing something that is more than the sum of the parts. That's the sort of idea of how that went on. So this idea, the whole is greater than the sum of the parts, became the defining definition of holism. Looking back, we can see that there is a sense in which that phrase fits the view of Nicholas of Cusa, and maybe also the view of Heraclitus. And it also fits the idea of holism in quantum mechanics, which is part of what I want to explain today. The idea is that we've got these positions, the whole is greater than the sum of the parts, and we have various manifestations of them in the literature. And these manifestations, unfortunately, when you scrutinize them, aren't all the same. In particular, and I want to stress this because people have been looking, philosophers, have been looking for antecedents of the idea of quantum mechanical holism, and have been looking for it in past utterances, for example, that of Heraclitus. Or you can find it in the Nicholas of Cusa quote. But Nicholas of Cusa is not saying the same thing that is in quantum mechanics, and nor is Heraclitus. To say that those who pay attention to the Logos, all things are one, is a different sense of holism than is the idea that if you understand the parts, then you understand to understand the parts is to understand the whole. To understand the whole is the only way to understand the parts fully. Those ideas are rather different. As is the idea, which is often used in this context, that everything is connected. Well, everything may well be connected. I'm not saying I doubt it. And that may be a form of holism, but it's not quite the quantum mechanical sense either. What I'm saying is, all of the past notions that we call now holism, thinking that they are, as it were, steps that lead us up to the quantum mechanical case, are different. They don't quite lead us to that same destination. The quantum mechanical case is quite different. Why? Because the quantum mechanical case says, suppose you have a whole that is composed of two particles, say two electrons. Suppose the whole is composed of those two electrons. That whole can have properties that you can't deduce in any way from the parts, the two component particles. It can have properties that go far beyond the properties of the two component systems. That's what quantum mechanics says. It says the whole, in this case two particles, is more than the sum of the parts because the properties of the whole can go far beyond any properties that are possessed by the individual particles. That's significant. Let me take you back all the way to the first of these lectures, to the example that I plucked from Plato, where Plato says, I think it's in the Hippias Major, Plato says, suppose you have two soldiers, say take, I don't know, Jack and John. Well, no, it doesn't work. Jack and Eric, or say something like that. I can't remember what names I used originally. Suppose you've got two soldiers. According to Plato, they can have courage together when they're together that they don't have when they are apart, when they are separate. Plato also uses another example which I don't particularly like. He says, suppose you have, well, one of the soldiers is simply one person, so he's got the number one, so we're attached to it. The other one is simply a soldier and has the number one attached to it. Together, however, they have the number two attached to them. That's his example, and I'm in two minds as to whether I think that's a good example at all. But I think the courage case is a good one, if we will go with the idea that two people, two friends who are comrades in, say, in the Homeric Iliad or something, they can have more courage when they're together, say Achilles and Patroclus or something like that. They can have courage when they're together more than they have courage when they're separated. There's a greater courage. That seems to be a holistic property of that pair. And it goes beyond the courage that they both have. So it does something more. It's an extra property that they have that goes beyond the idea of their courage separately or their courages separately. That's the idea. But that's not quite the quantum mechanical case either. The quantum mechanical case is you have a whole, the two particles, which can have properties that go far beyond the properties of the two particles if they were considered separately. And can be in an extreme form. By the way, the connection that they could have when they're together is entanglement or separability. They can have separability by themselves, but the entanglement can only come when you have the particles, in some sense, considered together as a whole. Holism then goes with the idea of entanglement. That takes us to what then is this? If we think of the Plato case, Hippias Major case, as some kind of step towards what we're going for, the whole is greater than the sum of the parts. It has properties that the parts don't have. You can see something of that idea in all of these things. But in the quantum case, it's quite a stark idea. Because in the quantum case, if you take the whole system, it can be entangled, but you can't find any of that, any trace of that idea in the two particles themselves. If you were to examine them, what you would you would find nothing that you could say about the two particles separately. So that idea that the two particles somehow they're making or contributing to this holism in some way, but you can't find that contribution in the two particles by themselves. In other words, it's not like the Plato case where the two people have, or the two soldiers have courage separately, but it's not quite enough. It's not the full courage that they have when they're together. In the quantum case, there's nothing there at the level of the individual particles. It's all in the whole. The whole contains all of that. Now, I want to try to give an idea of how that can be so. Let me try to explain a little bit about how this works in quantum mechanics, how holism comes up in quantum mechanics and what its relationship is to entanglement. When you have two particles, two electrons, say, when you have two electrons and they form, you take them as together, you're representing them on what's called a tensor product. A tensor product is really a product of two separate Hilbert spaces, which is how you represent each of the particles in Hilbert spaces. When you put them together and you want the representation of both particles in one space, then that's called a tensor product space. And it's indicated by this kind of cross here. Hope you can see this. As you can see, I do sort of sometimes miss the idea of a blackboard. It'd be a nice thing to have sometimes. This is indicated by this symbol here. So you've got two particles. This is the state of one particle, and this is the state of the other. Now, if you have an unentangled system here, the two particles are just two particles separately, then the entanglement, then we write that as this product. This is called a product state, because what it does is it represents the state of one particle and the state of the other particle. They're both taken from, as it were, the two particles. They go into this, but they're a simple product of these two. A simple product, and it's called a product state. Now, if you have a product state, then the particles are called separable. They're not entangled. The particles are called separable. If you don't have a product state, then the particles are entangled. That is the criterion for entanglement, that it can't be written as a product, and therefore that it's not separable. So there we have sort of the basic idea. Product states are separable. Non-product states are entangled. When you look at this tensor product, what you find is that it is vastly, this is the point to hang on to, it's vastly larger than the state of each, than the space of states of each of these two separately. So these may be two Hilbert spaces of, say, dimension 2, but the product can be vastly larger than any kind of simple Cartesian product. Now, Cartesian product is the kind of thing that you have in ordinary geometry when you draw an axis of lines, for example, this, and you look at this as the x-axis and this is the y-axis, that idea. When you have that, what you're essentially doing is forming a product space of two lines, the x line and the y line. And you're looking at all the things that can be determined as in that space as having an x and a y coordinate. So something off and onto the side may have x coordinate of 5 and a y coordinate of 3. Cartesian products are very simple products. You know and understand how to deal with them because you've done it in school for ages. You may only at the end of school have learned that what you are doing is graphing function that you're evaluating. And that is evaluated in a Cartesian product, because it was at least roughly René Descartes who formulated that idea of Cartesian product and Cartesian product spaces in order to represent functions. When you look at the tensor product space, however, it's not a Cartesian product. That is a very simple thing. If we were to look at this simple product, sure, we can think of that almost as though it's a Cartesian product, because you've simply got this thing, that thing, you can sort of represent it as, a point in the Cartesian product, because there's not much more to it than that. But the tensor product space has in itself much, much, much more than simply the states of one system and the states of the other system. It also has the states of both systems together, which are vastly more complicated, more than the two particles can have separately. That's where the entanglement comes from. It comes from the extra dimensions that you get in the tensor product space. And the extra dimensions of the extra product space beyond just simply the number of states that are in this particle separately from this particle, the states that are in that separately from this. That forms a very, very small class of the states of the whole system, because the whole system has states which are entangled and which are in the tensor product, and in which that tensor product has a much larger dimension than simply this kind of thing, which only has two dimensions. In the tensor product here for this, the number of dimensions is much greater. If you have a system which is entangled, in other words, which is not a product state, it's a different state existing in the tensor product, not existing, as it were, in the sort of just simply the two particles, the states of those that are just simply there, and you've sort of put them together in thought, if you like, or in name, but not really to make anything larger. That simple idea is only a fraction of what the space itself has available. What it has available is all of that stuff which is in the full tensor product. You can see that there's a little bit of Plato's idea there, but it goes not all the way. In the quantum mechanical case, the whole can be greater than the sum of the parts. In other words, that there is entanglement in such a way that the two particles separately cannot tell you anything at all about that entanglement. You can investigate them. There's no trace of that entanglement in each particle. There's nothing that says that it's there. Now you could say that in some ways about the Plato-Hippias major case, because investigate all you like the Achilles and Patroclus, you won't find that they have more courage together until you see them in action than they had separately. You won't find it in either of them. It's in both. And that's what makes that kind of relation go far beyond ordinary relations such as the idea of Alice being taller than Jane. That is really just simply Alice's height, Jane's height. You can't find out that Alice is taller than Jane from just simply knowing the height of either of them. But of course, if you know the height of both of them, then you can immediately deduce that, that Jane, say, is taller than Alice. In the case of quantum mechanics, no investigation of either particle separately tells you what there's no state that it has, and no pure state that it has, I'll put it that way. There's no pure state that it has, because in the case when the particles are entangled, the state of both particles separately are mixed states. And what that means is, in some ways, there isn't a definite state that they have. Investigate them all you like, and you can't find it. That goes some way to explaining what is happening in the Einstein-Podolsky-Rosen paradox. The two particles have a state, but it's a very rich state together. Together they have this very rich state. The state of the whole is very rich. Now, one person can investigate one particle. They can have a particle sent to them and they can get a result from that. Another person very far away can take another angle on their instrument and investigate the other particle. If the two particles were correlated initially, then no matter which axis is chosen, and they can be chosen at random, there will be a correlation of some kind between the outcomes. And that correlation of the outcomes is the thing which is encoded in the whole of the system, in the state of the whole. So when we say the whole is greater than the sum of the parts, what we mean by that is that there can be a correlation which the particles can have, which can be found when both particles are measured, which one could not find in the particles before they are measured, if you like. Before you have got to them, it's not visible. But that has to be a very, very flexible whole state that they have, because whichever way you measure them, however the alignment of the apparatus can be free of, let me put it this way, the apparatus can be chosen separately, completely separately, and yet there can be a relation which becomes manifest when the two particles are measured. I don't say that that relation is there inherently quite. I think the relation can make itself manifest when the particles are measured, but then if you chose another angle, another orientation of your devices, you would still find it. It has to be encoded for that continuum number of different orientations that the two instruments can have with respect to one another. That's what is going into that, the extra dimensions of that of the tensor product space. That's extraordinary. Now, you may want some backing on this, so you may want me to quote something, so I'll quote you from Hermann Weyl. By the way, the fact that there is this holism in quantum mechanics was first spotted by Hermann Weyl in 1920, either in 1926 or 1928, depending on whether one is looking at the first or second edition of Weyl's book on quantum mechanics and group theory. He says, he says, "It is true, therefore, that the state of a system consisting of two electrons determines the states of both electrons, but the converse does not hold. The knowledge of the states of the two parts of a system by no means fixes the state of the whole system. We find here a definite and far-reaching verification of the principle that the whole is greater than the sum of the parts. Now that quote is from Hermann Weyl, from a series of lectures that Weyl gave in 1931, I think, and it was called The Open World. It's the end, I think, of the first of the lectures, I think so. Don't quote me on that. But Weyl had also put this into his book, Quantum Mechanics and Group Theory, there he had actually gone into a little bit of detail, mathematical detail, as he didn't in this public lecture, as to how exactly that was going to work. And so you get more of a picture of how this quantum mechanical situation arises. So yes, there you have Weyl's idea, holism. I don't think he's ever been given credit for being the originator of the observation that there's a holism in quantum mechanics, but nevertheless it was him. And he did it very soon after the formulation of quantum mechanics, which, as I said, comes with I think it's called the Dreimann paper, three-man paper of Heisenberg, Born and Jordan of 1925. As I pointed out last time, we're in the 100-year anniversary of the origin of quantum mechanics, if you date it from the Dreimann paper. So only in 1928, I think, the reason I'm hesitant on saying this is because the first edition of Weyl's book is not available anywhere. And only the second edition is available, and it was the second edition that was translated into English. So we have access to the second edition. I've never seen a copy of the first edition. I don't think it's lodged anywhere. Such are the agonies of scholars trying to work such things out without any proper hints. Yeah. Anyway, it was Weyl who came up with this notion of holism. He quoted the idea, whole is greater than the sum of the parts. And he did it in the public lecture a couple of years later. Those ideas are profound, but they're not quite, they go far beyond what was called, or what we think of holism in Heraclitus, in Hegel, or in Nicholas of Cusa. Those are very different ideas, I think. You can still categorize them under the heading of a holism, kind of holism, but they're not the same. They're not the same at all. I think people are making a mistake, philosophers I'm talking about, are making a mistake thinking that there's a simple way of tracing the origin of quantum mechanical holism from the appearance of, either in Hegel or in Heraclitus or whoever you want to nail that onto. It's not the same idea. The idea in quantum mechanics goes far beyond what you have earlier. It's a little bit close to the Hippias Major stuff, but it's still not that either. It goes far beyond that. So, yes, there we have it. That's the idea. Now, the reason I'm saying all of this is because I think the idea of this kind of holism, all of them if you like, but all of these kinds of holism, are something that we need to add, that we need to understand if we're going to understand in a modern sense, if we're going to understand metaphysics. Because just as with relativity, holism is an important ingredient, and it subserves what we want to explain about particles, what we need to explain about particles as we find them. Now, I should mention this as the final point. This is not something that is often said, but it's worthwhile knowing. As you go up from 2 particles to 3 particles to 4 particles to 5 particles, you are jumping up in terms of the size of the tensor product spaces enormously. When you go up to 5, say, you're in a large dimensional space. If you're even just simply 3 particles, which takes you to helium, not even all of helium, just simply the electron shell of helium, then actually, no. 3 particles will take you to lithium. So 3 electrons. Not taking any account of the space needed for the neutrons and the protons, just simply the electrons, would take you to a pure space, a pure tensor product space, which has a pure product space, which is called complex projective space. 7. Complex projective space 7 would take you to, which is for 3 particles, and it would have dimensions of 14, which is 2 times 7. So the complex projective space 7 has 14 real dimensions and is the product space for 3 particles. So the size of the product space, even for just the pure states, not counting the mixed states, which is vastly higher, takes you up rapidly in the dimensions of the space. As you go up to 4 and 5, they jump up higher again, and the behaviors of the systems go far beyond what they are for dimension 2. For example, even for dimension 3, there are different ways that the 3 particles, can be entangled with one another. The entanglement, in other words, becomes a property of the systems. This is something that's sometimes said. The entanglement in the systems can itself be entangled. And that holds for 4, 5, 6 particles. Now, if you start saying, well, what about just one simple carbon atom? What's the dimensions of that? Huge is the answer. Huge. You'd have to have a tensor product for all of the electrons, all of the protons, and all of the neutrons. And you'd have to take the tensor product of all of that in order to get the state space, the pure state space only for all of those particles. That's going to be large. Now, if you start thinking about, well, what about all of the atoms? What about all of the atoms in your body? Well, the number of atoms in your body, the number of particles in your body is enormous. And the state space is going to be enormous, even much, much, much further beyond that. And what about a room full of people? What about a planet? What about the sun? What about all of those things together? What is possible in all of that? Well, the way that entanglement works, becoming more complex as you go up in the dimensions, suggests that there may be phenomena in those situations that we can't even predict at the moment. All of that may be something which will have to be worked out in the future. So with that I leave you, and that's why we should have it in metaphysics, because what bigger subjects are there for us to contemplate than these matters? This is where metaphysics should be. With that I leave you, as this 4th set of lectures was designed to do. It's designed to tease the idea that there can be a much richer metaphysics that we could be studying rather than what we are left studying now. Anyway, on that unhappy note, I will be back soon to talk about more of Nietzsche.